Okay, so now I've got here's some I made earlier problems. We've got a mass of 10 kilograms, a mass of 5 kilograms, initial velocities, a final velocity, and a final velocity we don't know. So this looks very much like it is an object number 1 and an object number 2, which are going to collide with each other and then move off separately from each other. So we've got M1, U1 there, M2, U2 there, M1, V1 there, M1, V2 there. So I'd write down my statement: in the absence of external forces, the total momentum before the collision equals total momentum after the collision, and then I can do my algebra. M1, U1 plus M2, U2 equals M1, V1 plus M2V2. Did you catch the deliberate mistake up here? Yeah, it wasn't deliberate, it was just a mistake. So that would be 10 times 6, 10 kilograms times 6 meters per second, plus 5 times negative 4. Now, why did I make that negative 4? I made it so that I could introduce another very important idea, or rather reintroduce it. Remember, we're dealing with velocities here, because velocity is a vector and consequently momentum is a vector. So we're going to say that if something is going to the right, it's positive, and if something is going to the left, it's negative. So in this, U1 is positive, so it's going that way, and U2 is negative, so it's going that way. So this is why these two objects collide. They're moving towards each other. Equals mass of the first one, 10, times its final velocity is 2, plus mass 2, 5 times V2. Now, you can see there that what we have is an equation with only one unknown, so we just need to apply some math skills and we're going to get the answer. 10 times 6 is 60. 5 times minus 4 is minus 20. 10 times 2 is 20, and that apparently equals 5 times whatever V2 is. 60 minus 20, that's 40, equals 20 plus 5V2, and from there, if you don't get V2 equals a 4 meters per second, then I'm afraid you need to practice some of your arithmetic. Another example, this time we've got those same masses, because basically I'm not exercising much imagination, same initial velocities, but only one velocity afterwards this time. So this looks like a scenario which, if we read the full question and had all the details and maybe a little picture, would look something like this mass plus this mass are moving along, they collide with each other, and then they stick together afterwards. So M1, U1, M2, U2, M1 plus M2, and a common final velocity. So put my statement down: in the absence of external forces, total momentum before collision equals total momentum after the collision, and then do my algebra. So let's see, M1 U1 plus M2 U2 equals M1 plus M2 in a bracket multiplied by the final velocity V. So 10 times 6 plus 5 times minus 4 equals 10 plus 5V. So 10 plus 6 is 60, 5 times 4 is minus 20, plus minus 20, equals 10 plus 15 times V, 15V, so that's going to be V equals 40 over 15, which is 2.67 meters per second. And since it's a positive value, that's to the right, as was this one up here, to the right. There we go. Some more fairly typical problems. This time we've got a mass of 10, a mass of 5, still no imagination being displayed by Mr. McCann here. Initial velocity of 6, only one initial velocity, so for this one it must be mass number 1, mass number 2 stuck together, and then off it goes. After the collision we've got a V1, not a U1, and a V2, not a U2. So they're moving separately after the collision. In other words, they have exploded away from each other. So 1 and 2. So there's my m1 plus m2 with a common initial velocity of u, and m1 v1 and m2 v2. So time for the algebra. After I've done my statement, in the absence of external forces, the total momentum before the collision equals the total momentum after the collision. So m1 plus m2 u equals m1 v1 plus m2 v2. So here we go. 10 plus 5 is 15 times 6. That's going to be 90 equals, plugging the numbers in, that's 10 times, apparently v1 is negative 1. Okay, minus 1 plus m2, which is 5 times v2, which is what we're looking for. So 10 times minus 10 plus 5 times v2. So take that minus 10 over there, it's going to make that 100, divided by 5 is 20, so v2 equals 20 meters per second. And it's a positive value, so it's to the right. Now, it's not just velocities that we can work out with momentum, we can work out masses as well. And this time we've got 2 velocities before the collision, 2 velocities after the collision, so it's 2 separate objects that strike each other and then move away separately from each other. We've got the mass of one of them, we want to know the mass of the other. Believe it or not, this is quite a lot to do with how we find out the mass of particles. It's a bit more complicated than just a momentum equation, but it's essentially the right idea. You'll notice this time I've skipped saying, in the absence of external forces, total momentum before collision equals the total momentum after collision, because frankly, by now, that should be burned into your brain and should be the first thing you write down every time you see a momentum collision. You'll also notice that this time I have not done a little sketch, because again, the fact that you've got masses, 2 initial velocities, 2 final velocities should be enough on its own to tell you that this is the form of the equation that you want to be using. So let's plug the numbers in. M1 we don't know. U1 is 4, okay. M2 is 5. U2 is minus 4, okay. And then M1 we still don't know, but it's now times 1, okay. Plus M2 is still 5 and V2 is 3. So 4 M1 minus 5 times minus 4 is minus 20 equals M1 times 1, okay, plus 5 times 3 is 15. So as with all algebra that you've been learning in maths for years and years and years, we want all letters on this side, all the numbers on that side. So let's move them around. 4M1, take that M1 over to there, minus M1 equals 15. We're just leaving that alone, not doing anything with it. The minus 20 will take over to this side where it becomes a plus 20. So that's 4M1 minus M1 is 3M1 equals 15 plus 20 is 35. So M1 will equal, let's see, that's 11.67 kilograms, because 11.67 is what you get when you divide 35 by 3. And if anybody writes to the right because we wrote that for all the other ones, then I will be annoyed. It's a mass. Mass is a scalar. The reason momentum is a vector is because it's the mass multiplied by the velocity, and the velocity is a scalar. Okay. Last 2 classic examples coming up. This time we've got 2 velocities before, 1 velocity afterwards, a mass before, we're missing one of the masses before. So it looks like we have got this time 1 and 2 which collide with each other, and we end up with 1 and 2 stuck together. And this kind of thing is very important for things like making sure your space capsule docks with the International Space Station properly and doesn't collide with it. So we'll have M1, U1, M2, U2, M1 plus M2, V. Oops, don't want that down there. So that's going to give us M1U1 plus M2U2 equals M1 plus M2V. So plugging the numbers in, 10 times 5 plus, we're trying to find out M2 times 2 equals, let's see, that's 10 plus M2 times 4.5. Ooh, never like it when we've got decimals. Oh well. 10 times 5 is 50, plus 2M2 equals, now multiply out the bracket, 10 times 4.5 is 45, plus 4.5M2. And then let's get all the letters over this side, all the numbers over that side. So that'll be 2M2, take this over to here, minus 4.5M2 equals 45, take the 50 over to there, minus 50, so negative 2.5M2 equals negative 5. Thank goodness we've got negatives on both sides, so they'll cancel out, because the last thing we want is negative mass. That would be a sure sign that something has gone wrong, and that should be 2 kilograms. And last classic example, we've got a mass we don't know, 2 kilograms for the other mass, 0 meters per second to begin with. So this is something just sitting on the table, minding its own business in 2 pieces that are joined together, like the 2 bits of the cannon shell for General George Armstrong Custer, or 2 bits of a toy that are held together by a spring ready to unleash on some unsuspecting person when they open a can. And we'll get a velocity for one object, a velocity for another object. We'll have an m1 v1, an m2 v2, an m1 plus m2 times u. So let's just show exactly how this ends up being a special case of the third way in which momentum can be written down as an equation. We've got m1 plus m2, u equals m1 v1 plus m2 v2. Well, if u is 0, it doesn't actually matter what the masses are. And plug the numbers in, but it doesn't matter, because m1 plus 2 kilograms for m2 times 0 means that everything on the left-hand side is 0 anyway. So let's get the right-hand side sorted out. m1 is what we're trying to find out. So m1 times negative 3. That's going to give us something interesting. Plus m2, that's 2 times 6, which is 3m1 minus, plus 2 6s are 12, so 0 equals 3 times something plus 12. You've been doing things like this in maths for years, so that means that 3m1 must equal negative 12, which means that the mass is negative 4 kilograms. Something's gone wrong. Think about it. What's gone wrong? Have you spotted it yet? Have you? There. That was a minus 3 meters per second. So that must be a minus there, which is a minus there, which means that's a plus. This is the most common mistake in momentum questions, in solving momentum problems. Forgetting the direction of the velocities involved, and therefore losing or gaining minus signs that shouldn't be there, and consequently your calculation goes wrong. So guess what the most obvious trap for the examiners to set you is? Yes, the most obvious trap for the examiners to set you is that one of the objects is going in the opposite direction to the other, so you're going to have to remember to put the minus sign in, and then carry it through the calculation properly to get to the right answer. The last thing that I want to include in this video is what I call the momentum decoy. It's a really, in my view, it's a really cheap trick, but the examiners do like to use it quite a lot. So you have some object, it might be a box full of sand or clay or plasticine or something. You've got this box type object here suspended from cables, free to swing. And you have some other object here. It could be a bullet from a gun, it could be some kind of test rocket or a test crash seat or a dart or something. But anyway, mass of this object, let's call it d for dart, with initial velocity D for dart, hits this large container, which we'll call MC for container, whose initial velocity is 0. And after this collision's happened, the scenario is that the box has swung upwards up to about here, say. So it's gone its little ropes of gone whee, and the dart is stuck in it. The dart or the bullet or the test rocket or the crash seat or whatever it is has been stuck into it. And I call this the momentum decoy because you're given masses of objects, you're given initial velocities and so on, and you're asked usually something along the lines of how high does that travel, or if you're given the two masses and you're given the height that it travels, you might be asked work backwards to find the initial velocity of the dart or the rocket or whatever it is. This is the momentum decoy because it looks like momentum, but you need to use conservation of energy to solve this. Conservation of energy, not conservation of momentum. You might at some later point in the question that rolls on from this use conservation of momentum, but initially you would need to use conservation of energy, which is to say the kinetic energy of the dart, a half mv squared, is going to, when the dart embeds itself in the block here, equal the potential energy that is gained by the block rising through this height h. And the trap is, it's not the mass of the block, it's the mass of the block plus the mass of the dart. So C for container, D for dart, G for gravity, H for the height it goes up through. That's the trap. So the decoy is that they set it out in a way that makes it look like momentum. The trap is seeing who forgets that if this dart is stuck in the block after the collision, then the mass after the collision will be the combined mass of the two. And then that kinetic energy is equal to that gravitational potential energy. So if we measured the height that it rose through and we knew what gravity was, nobody's mentioned a different planet, so we'll take it as 9.8, and we know the masses of the two objects, we can eventually work our way back to get the initial velocity of the dart using the conservation of energy formulas. Then at that point, we might want to work something out using momentum. But initially, it's conservation of energy. And that's your momentum decoy. Watch out for that. The examiners love to put that one in. They'll find a way to do it. If it's not in the written questions, it'll be in the multiple choice.